Hey guys, welcome to Unit 9, Derivatives. This is kind of where we tie everything we did with limits, analytical graphical, continuity, analytical graphical, and go back to the first time that we talked about limits and how they interact with derivatives and what the definition of derivative is. For this particular walkthrough, I'm not necessarily going to go through each of the specific components. I'm just going to give you more of a graphical way of thinking about this. Now, I know it says don't use a calculator, and that is correct. The idea is you don't want to, but I'm going to show you a visual via Desmos to kind of give you an understanding what's going on here. Kind of maybe like a hint, if you want to call it a cheat, sure. So if we scroll down a little bit, goes over the definition of derivative, what it really means again, and just getting used to this notation is going to be super important, especially when it comes down to the different ways you can denote it. You've seen this f apostrophe x or f prime of x, y prime as well. This middle section here, the d of f of x in terms of dx, that's going to be important later on as well. So just get used to all the different ways of seeing it, or dy of dx. And just saying that when you take derivative, you're finding a derivative in terms of x. We'll get to points where you sometimes take the derivative of another variable. Whole different story when we talk about higher order derivatives, but we'll get there when we get there. So in the first step here, the goal is that you draw the graph meticulously and carefully, given that that's going to take a little bit more time than I want to right now. I'm going to show you how you might see it once you graph it out. So cheating, we now have a graph here. And so the idea is that we want to make sure that sort of clean, very smooth upward transition from x equals 0 all the way up to x is 7, 8, 9, so on and so forth. Now the graph that you're given only goes up to about 3-ish because you can't really graph 4, 16. So just go up to x equals 3, but at least in the positive end, you want to get that nice smooth curve, just as if you were using it on Desmos. So the reason I'm doing it here is once you have it graphed out really nicely, you can then start making the connections between what the next steps are. So then in step 2, it says look at the point 1, 1 on the function. So I'm going to look at the point 1, 1. Okay. And so at that point, what's going to then ask you is find the derivative at that particular point, 1, 1. Well, what is a derivative? Go back to the definition. It's the slope of the tangent line to that function. The curve looks like a normal quadratic, right, your parent function. But if I were to draw a tangent line going through that point to the function itself, what would that roughly look like? So if I were me and graphing this out, more or less, over here, scrolling up just a smidge here, let's just pretend I did a decent job, right? And I'm going to ask you guys to make sure you do a decent job here. The goal is, if I have the point, you want to try to find that tangent line that kind of hits there. You want to do the best you can to get there. And again, the next part is just basically guessing what is it looking like. I know the answer because I know the shortcuts and I know the cheats and kind of how you navigate derivatives without having to do this graphical approach. But let's take the graphical approach. What does the slope look like? And when you take it out here, and I can kind of mess around with it, I'm going to give you the first one just to help you out here, and you might see the pattern here. The function is going to look something like this. Let's just make sure I get it down. Good to go. I believe it's going to be this. There we go. That's it. So you notice that the purple line is tangent to the red line itself. And so I can clearly see, well, what is the slope of that purple line? I kind of cheated because I already knew the answer here, but it's 2 times the x value of 1. So the slope here is going to be 2. And hence where you go from there and writing that down. Try this again with the next couple of points, and hopefully you see the pattern that goes from there. I can say, hey, let's look at 2, 4, right? If I look way up here, what does the slope of that line look like? The hint is the slope is not going to be 2, it's going to be a little bit different. But play around those numbers and you will slowly begin to see a pattern. That's the idea. Tying this in, once you get through this part right here, then becomes the fun part of actually calculating the derivative graphically. And so here is how I kind of walk through it in the notes. Let me just show you another way to go about it in case these written instructions are a little confusing. So let's take the point 1, 1. And let's take another point. Let's just say the 2, 4, 1. Let's take that one, right? Or I'm going to make it easy for myself. Let's do this. It's the same idea. I'm just using Desmos to help me out here. Okay. I'm going to cheat a little bit as well. I'm going to say, let's call this A. That's going to be f of A. Don't worry about the little cheats here. This is just to help me figure things out a bit more quickly. Okay. So if I move here, come on, come back. Okay, let's change the steps here. Let's make sure it's between 1 and 2, and steps we can elaborate. So what's going to happen is you see my purple point at 1, 1, and then you see the black point here 2 comma 4 currently, right? I can move the slider and it'll change it, right? My questions during the notes is going to ask you to find out what is the slope between those 2 points. You should know this, basic algebra 1, find the slope between those 2 points. And then I'm going to ask you, hey, bring that point a little bit closer. Now find the slope. Hey, bring the points a little bit closer to each other. Now find the slope. You see the repetition here, right? What we're trying to do is we're trying to get the 2 points, the distance between those 2 points as close to each other as we possibly can. And so just to kind of cheat a little bit here as well, we're going to say that g of x is going to equal, let me just make sure I got this right here. It's going to be, I believe, something like this. Pi of x. And then we're going to subtract. Okay, I'm going to just give up on that for now. Let me just do it more visually at this point. So you can imagine in between those 2 points there's a line that's created, right? And we can find the slope of that line. And we call it the secant, because the secant goes through 2 parts of that red function. And so as you go through the notes, you're going to see that we're slowly pulling this closer and closer and closer together. And slowly that secant line, hopefully, as you get really, 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 really close, turns into the tangent line. That is your goal. I also go to the negative side because you can either go from the right side and pull it in, or you go from the left side and pull it in. Either way, it doesn't really matter. Whatever visually works for you, that is the point that we're trying to get across here. So walk through that here. Take your time with it. Go through it step by step. And that will then in turn lead you to the final actual definition of derivative, which is what we got going on here. So let me just break this down into simple terms. Literally, this equation that I just circled for you here is basically what I just did 2 seconds ago. Okay. The only difference now is we need to deal with this new variable called delta x, or as we call it, the change of x. So let's go back here. Let's pull up the same representation one more time. Okay. So we can see here we have our 2 points, right? We have 1 point at x equals 2 and 1 point at x equals 1, right? When we say the change of x, what I'm asking is what is the difference of those x values? Oh, those differences of the x values is just 1. So I would say here the change between the purple point and the black point in terms of the x value, the change is 1. What's going to happen is what I'm asking you to do according to this limiting function, or the definition of derivative here, is as that delta x approaches 0, as the change of x approaches 0. So here the change of x is 1, right? If I pull it here, like that, the change of x is 0.5, right? The distance x-wise, on the purple point to the black point, it's 0.5. If I go over here, the distance between the 2 points on the x values is 0.25. As the distance, or the change of x, as the difference of the x values gets closer and closer to 0, what do we notice about the slope of the tangent line? If you notice here, this formula right here is basically the slope of the tangent line itself. You might not see the fact that this is actually the same thing as the slope definition, but if you go back a couple of notes where I kind of talk about this, and I think I did talk about this in, might be notes 1 or 2 from Unit 8, where we introduced the idea of derivative. I show in that video there basically how this formula kind of plays out, but the idea again is you're finding the slope between the 2 points as that change of x, as the distance of the x values gets closer and closer together. What happens to the general slope of the secant line, which then becomes the tangent line in and of itself. That is the essence of a derivative. You're finding the slope of the tangent line. This is graphically how we do it. You'll see that what I just circled here, this is the analytical way of going about it. And then you'll figure out as time goes on, later in this unit especially, you can find the derivatives function very, very quickly by some patterns that mathematicians have come up with and make things easier. You're going to definitely ask me afterwards, Mr. Park, why didn't you just tell us the shortcuts in the first place? It makes it 20 times easier. Is the point for you to understand the formulas, or is the point to understand the concepts? Both are important, yes. But if you just start with the formulas, you're just going to memorize it without understanding what happens behind the scenes. We start with the concept graphically, analytically, then we shift our way towards how the formulas help us out. We're not at the point where we need to necessarily use these formulas very quickly. Again, the point is get the concept down first, and then we use the formula as we go on from there. Okay? Limits will still play a huge part. Continuity is going to play a huge part as well, especially for notes number 1. I guess this technically is note 0, if you want to call it that. But as you get to day 1 content, those 2 concepts will come into play. So go back to Unit 8, redefine limits, redefine continuity. Make sure you're really comfortable with that before we move on. I can't stress this enough because calculus is, at least for me, it was the first class where I really struggled. And again, maybe that's a humble brag, maybe it's a flex, I don't know. But the point is that if you don't get the concepts now, you're going to be really lost when we start doing higher order, higher order differentiation. When we talk about implicit differentiation, integration maybe for a little bit. Those are the abstract concepts we get into. So make sure you know these basic ideas now, the concepts now, before you move on from there. That should cover for today. Go through the notes, ask questions as you need, and you should be squared away.